Well, good morning to the B cohort for AP Physics, the year 2021. And you are unfortunately getting probably the less engaging side of the bargain today, but turnabout's fair play, and on Friday you will get to have the fun and hijinks that the A cohort is experiencing today in your absence. So today is Groundhog Day. Hopefully we won't have to repeat this year, just like the movie. It'd be nice not to repeat kind of what we're going through, but we'll move on from that. We'll try to take a positive spin on things. Today we're going to look at springs and energy conversion, and we are going to implement some stuff that we have been working on, and a lot of it is just familiarity and just getting comfortable with the fact that, hey, I can convert work and energy. It doesn't matter if it's potential or kinetic. If it's potential, it doesn't matter if it's gravitational or elastic potential energy. Either way, it's going to work out just fine. So I'm going to do 2 demonstration problems and then release you to solve about 6 problems on your own for your assignment for today. And then just submit that when you can within the next day or so. And we'll move on from there. So 2 demo problems. And if I'm getting boring, you can speed me up to twice the speed. If I say something you don't understand, pause me and work backwards. So I'm doing a couple demonstration problems out of the book. The first of these is problem number 39 out of page 161. And the situation depicted there is the fact that you've got a gun that is pointed vertically. It's a toy gun. We're not going to bring a weapon into school. And the launching mechanism is compressed 0.120 meters, which is the equivalent of 12 centimeters. And it's going to launch a 20-gram ball to a height of 20 meters. The question that they pose to us is, what is the spring constant if that is the case? Well, we are going to determine this by first figuring out what the problem is giving us. Okay, these are the values that it's giving for us. But the key juncture in any time you try to solve these problems is just trying to figure out how to solve it. We're looking for the value of K, the spring constant, which is going to help provide that potential energy to launch it to that height. So what we have to know is that this toy gun is going to have an initial amount of potential energy that's going to be tied up in that spring by compressing the spring. Now here's what might be a little bit confusing. It's also going to have potential energy from its equilibrium position. It's actually below its equilibrium position in this case because you've compressed the spring in a negative y direction. So actually to reach equilibrium, you have to overcome that initial deficit in your potential energy due to gravity. Now that in turn, those 2 potential energies, when I add them, are going to equal my kinetic energy passing through the equilibrium position. And it's that kinetic energy which is going to end up giving it its final potential energy. Now, the convenient thing for us is that we can totally bypass the mediary here and jump right from one to the other. We don't need to worry about that. We can jump straight from one to the other, which can be kind of convenient for us. So let's mosey on down this path of knowledge here. The potential energy of a spring is 1/2 kx squared. That's an old friend by now. Notice I'm going to have a negative mgx. It's negative because I'm below my equilibrium position. I actually have a negative potential energy. And I'm using x instead of h here simply because that's the same value as this x that we're using to determine the spring potential energy. And that's going to equal my final potential energy of the height of this ball at the end. So now we just rearrange as needed. We multiply through by 2. I'm lumping together like terms. I've got an mg here and an mg here. I'm grouping together the h plus x. That's just for clarity's sake. And I'm going to divide by x squared. I've isolated my value for k. And now it simply becomes substituting in. You see that it ends up being a little bit of a bean counting exercise here. The height, you'll see that in the long run, that 0.120 meters really doesn't have that big of an impact on its final potential energy. We're splitting hairs a little bit, but nevertheless, we're going to incorporate it in there. It really doesn't have that big of an effect on the final value of K in this case. But when you finally crunch the numbers, you're going to find out that the spring constant has a value of 548 Newton per meter. So that's that first problem. Here's the second problem. A toy gun, another toy gun. We get to bring them into school when it's toy guns and a physics problem. And this toy gun has a spring constant of 8 newtons per meter, significantly less than that last one that the Pirate launched. We're not going to let a little girl operate with that kind of a spring constant. We don't want any family emergencies to emerge. And this gun is going to project a 0.0053 kilogram ball. So the barrel of the gun here is 15 centimeters, and in this case, we didn't include it last time, but in this case, we're going to say that there's a force of friction that's acting along the length of this barrel that's going to be opposing that forward motion. So we need to incorporate that into this problem, because what we're looking for is the velocity that this projectile is going to leave the barrel if that spring is compressed by 0.050 meters. So here's how we're going to tackle that. We're going to launch past the givens. They're up there in the problem. You guys know how to do that by now. We're looking for the final velocity. So we know that the initial potential energy that this spring is going to have is going to create this kinetic energy. But some of that potential energy is going to be lost due to friction also. So no matter how much I have potential energy on this side, I'm going to lose some of it due to this work due to friction. So I'm not going to get all the kinetic energy I'd want out of it. But we're going to flesh out each of these major concepts here. So 1/2 kx squared is going to equal 1/2 mv squared plus my force of friction times the distance along which that friction is acting. I'm going to multiply through by 2, simplify things a little bit, and I'm going to get and try to isolate my v by itself, and I'm going to say that my velocity here equals kx squared minus 2fd, I'm tossing it over there, divided by my m, but I also need to remember to take the square root of this puppy here. Okay, so that's what I've got. Notice that if I have a bigger mass here, that's going to have a negative impact on my velocity. Substitute in. Don't forget my square root sign. And we've crunched these numbers, and so we're going to find out that this projectile will launch at a velocity of 1.4 meters per second, which should not be enough to injure her younger brother in this problem. So these are just two little sample problems showing you how energy can get converted, how work has to be incorporated into it. And there's a lot of ways that you can set up problems that are going to involve all of these concepts. So you're going to show me that you've learned this a little bit, and these are problems that I would ask that you tackle prior to class tomorrow. And then what you will get to do on Thursday and Friday is what the A cohort has been spending their time on the last couple of days. And I think those labs will make a lot of sense when you get to them in the class. Okay, so these are the problems I'd ask that you tackle for tomorrow, and we will see you tomorrow on Wednesday. We're going to talk a little bit about the difference between kinetic energy and momentum. We were remiss in skipping that prior to Christmas break, or prior to ending last semester, I should say. So we'll make sure we tackle that. But we're going to call it a day. That's what we need to tackle, and good luck working on those. If you have any questions, don't hesitate to get in touch with me.